Well, good afternoon to everybody that's over in the UK. Good morning to everybody that's here in the United States. My name is Eric Tarr. I'm going to be leading this workshop for you here. I'm excited that all of you would take some time out to join this workshop, and hopefully we can cover some fun stuff and build some cool plugins and learn about analog modeling along the way. So this workshop, just to talk about some of the logistics of it, it's going to last for the next 3 hours. I have the workshop broken up into 3 different sections, and so we'll take some breaks at the top of each hour, one an hour from now, and then another one an hour from that, just about 5 minutes long breaks for those things. I'm going to try my best to get through the material so that by the end of the workshop, we'll have a functioning plugin. JUCE plugin, that's our goal. And we'll have to see how that goes. I've got some resources already prepared ahead of time. If you're wanting to follow along and you haven't already, there is a GitHub repository for this workshop that let me switch over and show you where you can access the materials if you haven't done so already. So on GitHub here, if you go to this link, github.com/Eric Tarr Belmont, from there, you can click on this repository called TS Pedal that we're going to be using for the workshop. And if you're familiar with Git, go ahead and clone that and have it on your local computer. Or if you're brand new to Git, just download it and unzip the package and be able to go off of it there. So I do have 2 branches that are set up. The main branch is the starting point where we're going to be adding stuff into the plugin as we go along. But then I also have a second branch called the completed plugin that if anything goes awry, that we have a version of this working that you can use and access from there too. Or if you want to see what the code looks like at the end, you can find that too. So that's the main thing to be able to work off of, because I've got a lot of stuff added in there already for us to use. And what it ends up looking like, this JUCE plugin, when you build it, you pull up Logic. So you can see kind of the end result. So we're going to be looking to build this Ibanez Tube Screamer modeled pedal. And I have some graphics set up for the plugin already. We're just going to be adding in the DSP code for it. And our goal is to get I apologize if my Zoom just dropped out. Hopefully I'm back in, and we're just going to continue on. So let me share my screen again. Hopefully that doesn't continue to be an issue with what we're doing. If anyone can update me with stuff in the chat, hopefully we'll be able to move forward without any more technical difficulties. So if you've been able to clone this on your local computer, you should have a folder on here to use that has the ProJuicer file in it, and also some source files. You'll find some of the common ones anytime you create a JUCE plugin, and also some additional ones for ones that we're going to add code to. I'll also add that as part of the repository, I've included some of the notes that I'm going to be following. In fact, there's probably more material in these notes that I'm going to have time to cover. In fact, I know that's going to be the case. So consider this just some additional resources that you can look over after the workshop is over. They're split up. Basically, the first section of the notes is on linear circuit modeling, and the second section of the notes is on nonlinear circuit modeling. So we're going to be doing two different sections of the tube screamer today. Then I also have a bunch of MATLAB code that can go along with the workshop that we're not going to be covering. This isn't a MATLAB workshop, but kind of the story and the background of the material that I'm covering is, one, I teach this as a semester-long class at a university. So I'm based in Nashville, Tennessee, and I teach at a school called Belmont University. I have a graduate class that just covers analog modeling, different techniques for it. So I have a lot of those resources and notes that I've done for my teaching for that. And then also this past spring, I gave a weekend workshop, a virtual workshop with the University of West London, and basically went through this same material over the course of like 16 hours in 2 days that now I have to shrink down to 3 hours for the ADC. So we're going to be skipping over a lot of this stuff in the notes, but you'll see lots of the stuff that I'm covering in here, and I'll probably even refer to it throughout the workshop. So basically our workshop is broken up into 3 sections. One is going to be the circuit analysis background. So I'm assuming that people don't have any experience analyzing a schematic, and we need to kind of cover some of those basic things and ramp up from very simple things to things that are more complex. During the second hour, we're going to go through and just focus on the tone section of the tube screamer. Then our last hour will be on the clipping section of it. So that's where we're headed. The goal of the workshop is for us to look at different ways that we can take something that's an analog system, so something that is a hardware effect that takes some input and some output, and turn that into a software system. So an effect that takes some code as an input and spits out some code as its output. There are many different ways to do this, but we're going to focus on a specific one. We're going to focus on component type modeling. So we're not going to focus on black box modeling on it. Our goal is to do a physically informed analysis of this and try and see if we can model or take these different components that are part of a schematic and turn them into digital code for it. So there are even many different ways that this can be done, and we're going to be focusing on one specific way of doing component type modeling called nodal analysis, but there are other ones that are out there worth exploring if you're interested in analog modeling. So one is wave digital filters, and we're not going to be covering that here. That's a very different paradigm for doing circuit analysis, but if you're interested in it, check out Kurt Werner's thesis, PhD thesis, and a lot of his stuff in DAFIX, that conference. And for us, we're going to be focusing on this nodal analysis technique, and also specific type of doing that called the Discrete Kirchhoff, the DK method of doing it. So if you're looking for more resources after this conference to supplement what I'm presenting here, those would be the types of keywords to search to learn about more. Okay, so let's pull up a schematic here to look at what the tube screamer looks like and kind of put our end goal in sight and then work backwards from there to start from the beginning. So a good website to know about for these kinds of electronics circuits to check out is called Electrosmash, electrosmash.com. I think I have the link to that down here. No, it's not in the repository. Sorry about that. So we want to go to Electrosmash and pull up the pedals tab and find the Ibanez tube screamer one right here. So there's lots of other ones that are on here that you could check out after the workshop and have your hand at working on those. This will not be good if you can't find this website all of a sudden. Well, I'm not sure if I can't connect to the internet that way, but I'm going to let's not worry about that for now. We're going to move on and just start talking about circuits. And hopefully I'll be able to get back to this website here soon. So let me switch over and start doing some notes. So part of this workshop is going to be programming in C++ using the Producer and Xcode. And part of it is going to be, me doing some notes here on paper or referring to some notes that I've already written and going through some of the math there. So let's start out and look at a very basic schematic and talk through some of the things we need to know about working with circuits and understanding them and analyzing them. So the most basic functional circuit that we can talk through is one that has something called a voltage source. I'll draw right now as a circle that has positive and negative terminals on it that then we can connect with a line that represents a wire. So in a circuit, we have a combination of different components and wires that all have to get connected together. And we'll take this voltage source and we're going to send it through this squiggly line called, we'll use to represent a resistor and connect it all together again. So a circuit has different things that we need to work with. One is a voltage source. For now, I'm going to label this as voltage that we'll call V for our input. So think about this in terms of a guitar pedal as a signal that's coming in off of an instrument cable that's getting plugged into our tube screamer pedal. And it has that prong, or the plug of that pedal has two parts. It has a tip and it has a sleeve. And those are going to represent the two terminals for our voltage on our input. You can also think of this, initially as just a battery. So if you're familiar with the 9-volt battery, it has two terminals. One is labeled positive, one is labeled negative. That's where our signal is going to be coming from. And our signal will be represented as a voltage as it goes through our circuit. And the other things that then happen is we have this wire to carry our signal through the circuit. And we have this resistor here, which is going to change how the electricity is flowing through the circuit. So this resistor here will label, and it's going to have a variable associated with it called R. So this is a resistance. And the different units that we'll find for these different components is we'll have volts for our source, voltage source, and our resistance is in ohms. And usually resistors will have values. If you were to pull up like the tube screamer schematic, you would have values in the range of like thousands of ohms usually. So this circuit will allow there to be the flow of current that we'll say that the direction of the current is going to flow from the positive terminal through the wire that then goes around, flows through our resistor, and then comes back in over here through into the negative terminal of our source. This could be a battery or some other kind of source. So the first relationship that we need to understand about a circuit is the relationship when you have a resistor and a voltage between these things in current. So first one is Ohm's law. Here, very foundational, important concept for circuits where we have voltage is equal to the current, I, times R. So electricity is this flow of electrons through the circuit, and the amount of the flow of electrons is based on our current. Voltage here is a force that's pushing those electrons through the circuit. You want to think of it as water flowing through pipes. You have a pump that's pushing the water through the pipes, and the amount of water that is flowing through is our current. And then we have something that's going to, block the flow or restrict the flow of water going through there. So if we had particular values of things for our circuit that we have over here, let's say our voltage that we have is equal to 9 volts, and we have some resistance here that's equal to, for now, let's just say 3 ohms to make it simpler on us. So we have 3 ohm resistor like this. What we would do is plug these things into our equation and say we have 9 volts here is equal to some current multiplied by 3 ohms, like this. And it's just algebra that we need to apply here in order to be able to rearrange this to solve for our unknown variable. And this is what circuit analysis is all about. You're going to have some known quantities as part of the relationships between these things, and some things that are unknown, and we need to solve for the unknown things. So in this case, we can divide by this 3 ohms, and we find out that our current here is equal to 3. So 9 divided by 3. I'm going to be going through this, and some of it is just off the top of my head. If I make any algebraic mistakes or anything like that, feel free to post in the chat or flag me down if I make any of those errors. But hopefully it'll be smooth sailing, and at least the concepts of it you can grasp from. So this is our very basic relationship between voltage and resistance. I'm going to introduce that there's also another type of source that we could find in a circuit that we will use as part of these things, and that's called a current source, which I'll indicate with a circle and a line through it. And so this is the case where we would have a different type of source that is introducing or controlling the electricity in here. And in this case, this current, this source tells us the current of the circuit. And so we could say that we have, 3 here for our current, and we would have 3 here for our resistance. And now the question is, well, what is the voltage that we have? Because that's the unknown thing. So in this case, the way that this is usually done in circuit analysis is you have these arrows going through for the flow of the current, and then the voltage is taken across some component of the circuit. So in this case, our voltage is taken from this side of the resistor down to this side of the resistor here, and we have some voltage that we're trying to find, and the same relationship holds. In this case, we're trying to find the voltage as a function of our current, which is known here. This is in amps. So 3 amps, and we have 3 ohms. And so now we're finding that our voltage is going to be equal to 3 times 3 equals 9 volts. So 2 different kinds of sources that we'll come across as in the workshop. Most of the time we'll work with the voltage source, but in the decay analysis, we will come across these current sources too. So the way to think about a source is it sets that there has to be a specific voltage that happens over this part of the section of our circuit. Or the current source means there has to be this current that goes around here, and then we'll usually find the voltage across it, or the opposite one over here. So in the case of this current that's flowing through the circuit, it is the case that we have the exact same current that's flowing through all positions here in our circuit, like this. Or in the case of this voltage, we have the voltage that is identical, whether it's over here in our circuit between these 2 wires going over here, all the way over to this side of the circuit too. So we have the same voltage from this point to this point as we do over here and here, and the same current right now going through all the wires and resistor over here of our circuit. So just some essential things to establish as part of getting started with circuits. So that we need to build off of this simple one up to something way more complex. So let me continue on and talk about a circuit where we add in multiple resistors, and we see some things about that. So let's say we have now our same voltage source over here. That'll be our input voltage. Then we have 2 resistors. So this is a very important one to talk through in several different ways. So here's our circuit. We have resistor 1 and we have resistor 2, like this. And we're going to have some current that flows through the circuit like this. That'll be our I. An important one to note in this case is that we will have the same current going through this entire loop of our circuit like this. We we have some voltage input, and we're going to go over here to some voltage output. So, we could define and say, this is going to be the output of our circuit that we're interested in. So now we're able to set up two different voltages that could happen at different places in our circuit. So there's one voltage that occurs over here between anywhere along this wire up until this resistor right here. And we're taking that resistant or the voltage down to this other wire somewhere along here as the thing that is defining our input voltage. But we have a different voltage that occurs over here because it's split up by these resistors. And so we're going to take some measurement of the voltage that goes from this point down to this one right here. These points that we have in our circuit, we can call nodes. That's just a node is a point that we want it to be, we want to uniquely define them between components in the circuit. Okay, so we have a node here that we'll have compared to this one down here, and we'll have another node over here that we'll want to compare to one down here. You might have also heard of this before if you've ever heard anything with circuits or dealt with electricity, even in your home or anywhere else, is that we have a reference node that we're going to call and say this is the one that we're going to compare it to, that we'll call ground. And in many cases, we will assume that this voltage right here is equal to 0. So keep that in mind as we're moving forward. Okay, so we have our voltage input over here. We have our voltage output, and we're going to want to look at the current that's flowing through our circuit as our way of figuring out if we know what our voltage at our input is, going to our voltage at our, we want to calculate our voltage at our output. So one of the rules to know about with resistors is if we have two of them together, like this, R1 and R2, we can temporarily combine them as part of our calculation and say that there is one combined resistance, I'll just call R, that happens to be the sum of these two resistors. So R1 and R2, like this. Okay, so temporarily, let's use that to our advantage over here and write this circuit as the one we've seen before. That has just a single resistor like this. And this will allow us to figure out our current. So what we want to do is have some R over here and now find our current. That current is going to be going through both resistors, and then we can go back through and plug it in to look at the other ones. So just for the sake of this example, let me plug in some values here for resistors. Let's call this one going to be a resistance of 4, and this is going to be a resistance of 2. Okay, so if we combine those together, our resistance is going to be 4 plus 2 equals 6, like this. So now what we have is some voltage at our input. Let's call this a voltage of 10. And we want to, let's call that 12. I changed my mind. It'll make our math easier that we're going to be doing here. So now what we need to figure out is this current that's going to flow through both of these resistors that we can use. So we had our relationship before. Our voltage input is equal to some current times our resistor R, which is 6. So we have 12 equals I times 6. So we'll do 12 divided by 6 equals I. Our current now is equal to 2. So that is going to be our current that's flowing through both of these resistors. And then we can go back and use Ohm's law to figure out the voltage that's happening across these resistors. So this one over here, we could say that we have some voltage input and some going over here and some voltage output, and we know the current. So V out is going to be equal to I times R2. So it's the voltage across this one is equal to the current through it times the resistance. Or in other words, we have V out is equal to 2 amps times 2 ohms, which is going to be equal to 4 volts. Okay, so we started out and we had an input voltage of 12, just some arbitrary number, and we go through some resistors, and now we have a voltage that happens at this section of our circuit that has a value of 4 volts. So this type of circuit that we've seen is actually a passive amplifier or an attenuator that takes some input voltage and it reduces it. If this is an amplitude of a signal going in, we can figure out that it's going to be less of that signal over here. The amplitude is going to be reduced for our output. So that's one way that it can be calculated. There's several other ways that we want to be able to analyze this circuit and understand it. So let me redraw it again, and we'll be able to confirm some of the stuff that we've found before over here. So say we have V in like this, going through some resistor, R2, this. R2, R1. Okay, so we've already found that our voltage here at our output is equal to 4, and we had some voltage over here that was equal to 12. We could, if we wanted to, because these are nodes that we've discussed before, 2 points in the circuit, we can measure a voltage that goes across this particular resistor 2. So let's call this VR1, okay? So we had that this resistor was equal to 4. So we're trying to say VR1 is equal to some current times our resistor R1. So our current that we found before was 2 times 4 ohms. So the voltage that goes across this one right here is going to be 8 volts. Okay, so that's another value in our circuit that we could calculate. This also brings up a very important point about working with circuits like this, is that this one right here has a special name that we'll want to know about called a voltage divider. Where we have some input voltage over here that's 12, and those 12 volts end up getting split across this resistor up here at the top and this resistor over here at the side. So we have this new relationship that we can write called Vn equals VR1 plus V out. Okay, so the idea is you start out with some voltage here and it gets split up across these two resistors when they're configured in this way. So that's the concept of a voltage divider. Sometimes this is also drawn where you have the voltage maybe from some point up here at the top. Let's say we have 12 volts up here, and then goes through some resistor like this, and goes through another one like this, and then we head down here to ground. So this is a circuit that doesn't have nearly the amount of detail in it as this one up here, but remember that this voltage is going to be compared down to here to something that is at ground, is this point over here in the circuit. And so if we have 12 volts up here, we end up having 8 volts get split across this resistor, and then another one down here for 4 volts. So you add these two things up, and it allows us to get this one over here. So this is another important relationship to know about. We don't have time to get into it too much, but there is also a circuit analysis technique called the mesh current analysis, where you look at loops. If you have experience with circuits, maybe that's another one you've heard about before, where we look at the voltages going through a loop like this, and they all have to add up and either be equal to 0, or the voltage over here is equal to these two over here. So just some things that I'll mention. A couple other things that we want to be able to do with this circuit and build off of is, let's say we want to write the relationship in a special form called the transfer function form. Like this. So what we can do is talk about the current going through this resistor, and then it has to be equal to the current going through this resistor, right? So I want to, let's say, trying to think based on what we know already, how to introduce this. So we know that there is, let me pause on this transfer function form and introduce something else that we'll want to use to come up with this transfer function form, which is this idea of a voltage drop. Voltage drop. I should have mentioned this before when we were talking about the circuit this way. So we have 12 volts here, and we end up having 4 volts here. And so what happens is between this particular node going over to this particular node, we have a drop of 8 volts to go from 12 down to 4. So we can use this as a way to describe, you know, the relationship that's happening at this point in our circuit to this one over here in our circuit as well. So let's say we have the current going through this resistor right here. We have VR1 equals the current I times R1. So VR1 is equal to 2 times 4, like this. We also know from this equation right here that VR1 is equal to, if we rearrange this, we have V in minus V out, like this. Okay, so now we can plug this in over into this equation and say that we'll substitute VR1 in over here and say V in minus V out is equal to this current times R1. And what we'll do is solve for the current and say that I is equal to V in minus V out over R1 equals I. So what we've done now is we've eliminated this variable up here, VR1, that we want to use, and substituting it in here. And now we have this relationship that's just based on our voltage input and our voltage output and that resistor for this current. So this is going to be an important form that we'll use over and over and over again when we're trying to look at the current that's going through some part of our circuit, is we can write it as the voltage change that goes from the point over here. We have the current flowing this way, minus the point over here divided by this resistor is equal to that current. So that's a very special way to do it that we'll use as part of this technique called nodal analysis, where we define these different points and call this one V in. We have this one over here that's called V out. These are the 2 nodes that we want to use. And so we can determine our current here going in this way by using this relationship. So let's apply that again and now be able to write our circuit into this transfer function form. That's the one, that's our end goal of what we're trying to get to. Okay, so let me write that out again. Like this, we have R1, we have R2. This is going to be our voltage for our input and our voltage over here for our output that we have from this node down to our ground. We have from this node down to our ground. Okay, so as part of this nodal analysis, what we're going to say is that the current that's going this direction has to also be the same as the current going this direction. We're saying that the current is always the same all the way around the circuit here. Okay, so the current going this direction we just looked at, which was this V in to V out, V in minus V out over R1 is equal to the current going this direction through our circuit, which is now our voltage drop is going to be this point here, our V out down to ground. So V out minus 0 over R2. Okay, so what we want to do is rearrange this so we can put it in a special form. Our goal is to write this as V out over V in, like this. So we need to rearrange the terms to make this happen. So let's put all the V outs on one side and the V ins on the other side. So doing some algebra, we'd have V in over R1 is equal to V out of 1 over R1. So move this term over to the other side, plus 1 over R2 like this. And we can multiply this term over to the other side. V in equals V out times R1 of 1 over R1 plus 1 over R2, like this. We can combine this term in here and say that V out is going to be equal to 1 plus R1 over R2, like this. And we can move this over to the other side and move the V in over to the other side. So V out over V in is equal to 1 divided by 1 plus R1 over R2. Okay, so this is an important form for us if we are trying to represent this as some code, that we could turn this into a piece of digital code that runs in our plugin, where we could say that our V output is equal to this whole thing, let's just call G, some gain multiplied by V in, okay? And in terms of our algorithm, normally we would write it as like our output at sample number in terms of our plugin is equal to some gain multiplied by X of n, okay? And so this is calculated based off of this relationship right here between the resistors. So we could set this up in our plugin and say, we have something called R1, we have something called R2, and plug these resistor values in and turn this into an algorithm in our code just by maybe in our plugin defining some R1, defining some R2, calculating some gain, and then applying that gain to each sample of our input signal to get our output signal. So lots of stuff to take away from this. One, the idea of nodal analysis and a voltage drop going from 2 points in our circuit, and then a way to write our circuit in a transfer function form, that is our input and it getting changed by some variable to calculate each sample of our output. So this is an essential one to get through for stuff we want to do. Want to see where we're at in terms of things in the chat, and see if I can get into ElectroSmash now. I think some issue with my internet. Okay, so tube screamer analysis. Let's take a break from circuit analysis for a second and talk about the things that we're going to be trying to model. So the tube screamer is this large circuit that has a lot of stuff going on in it. We are not going to do the entire circuit. We're going to focus on two particular sections. One is this tone section right here that has a tone control and the output volume control right here. And then the other section that we have is the clipping section. So during the second hour of this workshop, believe it or not, we're going to be able to go through this tone section. And then the third hour, we'll be able to go through this clipping section and analyze that. In the interest of time, rather than me continue to write out all these notes by hand, what I want to do is go and switch over to some of my notes where I have stuff already written out and talk through some of those things that we can use to quickly get from where we're at now with the voltage divider up to the things that we need to know in the second hour to be able to analyze this tone and volume control. So a few things to hit on this. So let me skim through to some parts, skip ahead to some things in my notes for this. So we just covered the voltage divider in transfer function form. Let's skip potentiometers for now, and we'll have to come back to them in order to be able to understand them. So we need to understand what happens when we put resistors in parallel with each other. So let me focus on this section. Sorry, it's kind of blurred out a little bit in the scan. So this is the case where we have a more complicated circuit where we have a voltage input that has a current that goes through this top resistor that then gets split into these two other paths over here, I2 and I3, okay? So our goal is to still write this as a function of V out over V in for our transfer function form, but it's gonna look a little bit different because we have these different resistor values, R1, R2, and R3. We have more things happening. So there's a few relationships that we can write about. One is that our voltage at our input is still going to get divided up here between voltage 1 and voltage 2. So that was our voltage divider equation. Vn equals the voltage across here and the voltage across here. And it's the case that if you can see my mouse up here at the top, this part of our circuit is a single node, okay? This part up here is a single node because there's no component that separates these parts until we hit this resistor, and this resistor. And that's going to be measured down here relative to this other point, which is our reference on it. So the voltage that we have across this resistor R2 is equal to this resistor over here, V out, okay? So that's another important relationship for it. So we can write it as Vn equals V1 plus V out. So the new thing that comes up with this circuit is, what do we do about the current? What do we do about the current? So we have a single current that's going to go through this resistor here, and then it gets split up into two different parts. So we have current I1 that goes into this node is going to get split into I2 and I3. So think about it, water flowing through a pipe, it encounters this joint in the pipes where it splits off, and some of the water goes down this direction and some of the water goes over this direction. So the new relationship to know about here is that we have I1, the current flowing into our node, is equal to the current flowing out of the node. So we have these two things here. That's our new relationship to be able to use. So we can go back to Ohm's law and use that and say, we'll plug in the value for I2 over here, which is going to be this V2 over R2 from Ohm's law, or there's also V out over R2 from Ohm's law. So we can plug that into our equation. And then we also have for I3 up there, Ohm's law is V out over R3. And we plug these things into that equation. And now we can figure out what it is compared to the I1 at that part of it over there. So if we plug those things in over here, we can substitute in for those things and plug and chug our algebra, and we get to the point of having our V out is equal to some gain over here times V in, and it just so happens to look like this time. Instead of just R1 over R2, we have this additional term R1 over R3 that's in the denominator. So again, this is something that we could write as our in our code as a calculation, that we have some G, that we just multiply each one of the values of our input signal by this G in order to be able to use in a process loop within our plugin if we know what those resistor values are going to be. So that's what our algorithm would be for this passive attenuator of a circuit. So the key thing here that we talked about was this idea of splitting the current up, flowing into a node, and whatever those multiple currents are, flowing out of the node. Okay, we need to talk about op amps. So let me skip ahead to another one that we need to discuss just to get some of the bearings for the way that an op amp is going to work. So this is our other component that shows up in our Ibanez tube screamer is we have this op amp, and this is a new type of device that has, instead of 2 terminals, it has 3 terminals. We have 2 that are used for the input and 1 terminal that's used for the output. This is also technically an active device. We supply power to it. So in the case of like a guitar pedal, what happens is we supply it with 9 volts. That's not really indicated on this schematic. At least the tube screamer is supplied with 9 volts on it. So the op amp is where we can actually boost the amplitude of our signal rather than just attenuate it. Up to this point, we've been talking about passive circuits. So whatever happens inside of our op amp is complicated. We are going to assume some ideal characteristics of it and be able to apply it then to our circuit as part of our algorithm for modeling it. So a few things to know about op amps. Let me find the things we want to know about it, some assumptions on it. So there's these 2 input terminals, the positive and negative terminals. We're going to make the assumption that those terminals have the exact same voltage, okay? So in some cases, we'll label this as a single node and say, you know, our voltage at the positive terminal is equal to the voltage at our negative terminal there, okay? And then we'll have another assumption that we'll make about it is that there's no current that's allowed to flow into our op amp. So it basically stops the flow of current through that section of our circuit. The current is allowed to flow around the op amp, but none of the current is allowed to flow into the op amp. So that's a thing where there's no current that is allowed to flow from the positive terminal over to the negative terminal on it. So just another really important thing to have there. Looking at the, someone can help the person in the Q&A. At the break time, I promise I'll be able to stop and help some people get the project being built on it. So we need to look at a few different examples here for op amps and how we can analyze them using nodal analysis. So here is a special type of, or a very common type of amplifier circuit where we have a voltage at our input and a voltage at our output on this. And then we have resistors in this configuration right here, where we have resistor connecting from our input voltage over to the negative terminal of our op amp. And then we have a resistor going from our negative terminal over here to the output of the op amp. And we're going to take the voltage from the output of the op amp down to ground, and that'll be the output of our circuit. So this is the one we want to be able to look at, the transfer function of our signal going from voltage of our input over to our output. So what we'll do is define a new voltage node right here in the middle, because this is distinct and unique compared to the node over here and the node over here. So we'll just temporarily define one called Vx. And an important thing that we can use from the assumptions about a way that an op amp works is that this node that we have going into the negative terminal has to be equal to the node over here for our positive terminal as well. And this one is tied to ground, which means that this voltage has to be equal to 0, like this. So anywhere we have Vx in our equations that we're going to write, we can substitute in 0 volts for it as a way to find the relationship between this V in and V out, okay? So we'll use this nodal analysis technique that there is some current that's flowing from V in over to Vx, and we'll write that as V in minus Vx over R1. That's our equation for the voltage drop that happens from this node to this node. Okay, then we have another current that we'll define going from Vx. It cannot go through the negative terminal, so we'll have it go from Vx over here to V out. And so there's a voltage drop that goes from here over to V out. And we would write that as Vx minus V out over R2. Okay, now, because there's no current that's allowed to flow into the op amp, we have a current flowing through this resistor, and all that current has to flow up here through the top. And that means our current I1 has to be exactly equal to the current I2. So we can set those two things equal to each other in our equations and have this one, Vn minus 0 over R1 is equal to 0 minus V out over R2. So if we get rid of our zeros, now we have Vn equals negative V out with these resistors. We can rearrange it to solve for V out and Vn. And so we end up with this relationship where we have our output, could be Y in our code, is equal to negative R2 over R1 multiplied by Vn. So this one's called an inverting amplifier, where the output voltage is actually the opposite polarity as our input voltage, because there's this negative sign that gets multiplied as part of it. So we can have an increase in amplitude in this case if we pick our resistors to be values that are such that this is greater than 1, right? Think of it as just digital gain, where if you multiply by something that's greater than 1, you get an increase in amplitude. If you multiply by something that's less than 1, you get a decrease in amplitude in your signal. So we just need to pick resistor values that will allow us to, if we want to have something greater than 1 or less than 1, it's up to us. Okay, so we haven't covered potentiometers just yet, so let me skip over that for now. We need to talk about filtering also here before we take a break. So let me finish discussing some of those things, and then we'll take a pause and come back and continue on from here to try and get into analyzing the tube screamer. So let's talk about filtering. I expect that maybe some of these concepts are more familiar to start about thinking about it as a digital filter. If people are familiar with digital signal processing, a simple way to create a filter is just to introduce one sample of delay in parallel with our input signal. And when you add those two things together for our output, this is going to create a low pass filter because it creates destructive interference at high frequencies and constructive interference that happens at low frequencies. So in terms of writing this as a function in our code, we would write it as something that looks like this, right? Hopefully you've seen something in a plugin that looks like this. You have some output sample Y is equal to some input sample X plus X of n minus 1. Okay, so this is a delayed sample. We need some way to store it into memory for just one loop and then be able to add it in. So as long as we can create this one sample of delay, then we're good. So this is an equation where we have to store the state of a value of our signal as it's going through. So it just so happens that like the state that we're storing in memory is the input signal, the sample that then we add in itself. We're going to be doing a similar thing when we try to create filters with a circuit. Is there's a new component called a capacitor that will store, as a way to think about it, it will store some memory of the state of the circuit from the past, and that will influence how it behaves at the current time that we're trying to model. So this is a thing called the difference equation, and we want to be able to turn our circuit schematic into a difference equation like this. So, if we were to, make this a little bit more sophisticated, we could add these coefficients, B0 and B1, and plug those in as multipliers out in front of these things here. And now we end up getting, more kinds of filter shapes that we could introduce. Let's skip ahead to what we need to talk about with the decay method, because there's some important rules that we're going to follow for how we treat some of these things. Well, I guess I need to talk about a capacitor to begin with before we jump ahead to that. So a new circuit element that we'll use as part of creating filters is a capacitor. So if you look at our Ibanez tube screamer, there's resistors, capacitors, and op amps are the main components. If we can understand some basic things about how they're going to work, then we'll be able to try and model them. So a capacitor is a way to think about it is like it's a resistor that depends on frequency. So for certain frequencies, it might have a high amount of resistance, and certain frequencies it might have a low amount of resistance. And how that changes will influence, the way that the voltage is or the signal is across that resistor for different frequencies. So, for instance, we could treat a capacitor like this as an open circuit, or I guess I haven't even talked about that, a really high resistor for low frequencies, which essentially blocks current from flowing through. If you have like an extremely high resistance on it, that would basically be a break in the circuit that doesn't allow current to flow through it. So this is something called an open circuit, where there's no current that's allowed to flow through it, which can happen if your resistor just is humongous. If you think about the relationship between V equals IR, there's no current will be extremely small in that case, no matter what the resistance or the voltage is going into it. So what this does for low frequencies is it doesn't allow the signal to pass through here. But if we incorporate that capacitor with a resistor, what ends up happening is we have the voltage input over here, and there's all that voltage at our input doesn't change because of the resistance, and we just have our V out is equal to our V in this case, when no current is allowed to flow through the circuit. So this is how we can use a capacitor to allow the low frequencies to pass through from our input voltage over to our output voltage like this. But the capacitor changes for high frequencies. Way to think about it is as you move up in frequency, that capacitor is going to have a smaller and smaller resistance all the way till we get to the point where at high frequencies, it acts as if it has no resistance. And so that would be something called a short circuit, where you're basically bypassing that component, and you basically just have a wire that happens there. So this becomes, in that case, just a single node, and we don't have any voltage that we can measure because there's no component over here to measure it across. So at high frequencies, our voltage at our output is equal to 0. So for low frequencies, our input goes straight to our output. And as we move up to high frequencies, our voltage at our output goes down to 0. So this is a way that you can create a low pass filter because you pass the lows and you cut the highs as part of it. In the case of rearranging our capacitor in our resistor like this, what's going to happen is our capacitor acts as an open circuit. So for low frequencies, and in that case, there's no current that's going to flow. So when we take the voltage across this resistor, there's nothing there that's left over. So we have nothing for low frequencies at our output. And then if we have the high frequencies over here, excuse me, that there's a short circuit that happens, then our voltage for our output is equal to the voltage at our input. So this will pass the high frequencies to our output voltage from our input voltage. So this is how we could use a capacitor, or how it ends up creating these different kinds of filters. What we're going to need to do is incorporate them in some more sophisticated ways for our tube screamer. But I think this is probably a good point to stop. I know I'm going at a breakneck pace, but I'm trying to squeeze in as much as I possibly can in the time. So let's try and take a 5-minute break. I need to get a drink of water here. And if there's some questions on the Q&A, I can try and answer them over the next 5 minutes. And then we'll get back together at whatever 5 minutes from now is in your time zone, and continue on from there. So now in this next hour, our goal is to get to the point of hopefully having some code that runs in our JUCE plugin to be able to do the tone section of the tube screamer. I am going to try and go through some of the mathematics and use the tube screamer as our example for doing the circuit analysis on it. But then, as things go along, ultimately we want to be able to put this into our plugin and hopefully get that working. So let me go ahead and see where we left off by sharing my screen. The main thing we need to talk about now is how we can take this capacitor and turn it into something that's very easy to discretize, which means something that we're taking from an analog continuous time system our circuit and be able to turn that into something that we can easily turn into a digital algorithm that we can run in our plugin. And there's been a lot of different techniques that have been done over the years for how this is done, using a Laplace transform that then you do the bilinear transform and convert that into the Z transform form of a transfer function on that. But there's been this one that's been, I don't know, around maybe for 10 years or so, that's kind of gained a lot of traction in audio modeling that we can use here that will make our lives, I think, a lot easier for doing this analysis. And it's called the Discrete Kirchhoff method. So I'll spend a few minutes doing some notes by hand because I think that this is actually very important to be able to talk through at a slower pace. So let me move my mouse out of the way here. Okay. So the Discrete Kirchhoff method, where we're going to just take our circuit and turn it into a digital model as part of the schematic straight away, rather than going through multiple steps in the analysis of an analog, then converting it to digital. You do it like this. So let's say we have our voltage source over here that goes through a resistor and then a capacitor like this. What we're going to do is make a substitution for anywhere we have in our circuit a capacitor. We're going to make a special substitution on it. Where we split the signal up into two parts. We have a path that represents the resistance, or a complex way of describing resistance is called impedance. So there's this resistance that happens of the current that's flowing through the capacitor. And then we'll add in something over here that is a current source, like this, which has the function of doing the storage or the memory of the capacitor for how it influences the current that's flowing through here. So what I like to do is label some of these things as like our state that we're going to remember. I'm just going to call this one X1. That this one actually matters at the current time. So it'll be over some sample number. And then we have a resistor that goes along with it and is paired with it for the capacitor. We'll call this R1. And then this one up here is going to be R2. Okay, so we have a capacitor. The units for a capacitor are in farads, but we have some value of this, usually on the order of like microfarads, nanofarads, picofarads, so very, very small amount of capacitance. Then we have some resistance up here that we want to use for it. I guess I'll just call this one R2. And what we need to do is take the capacitance that we have here from this device and calculate a new resistance from it and see how that influences the way that our state gets updated. So I don't have the time to go into the derivation for how this works. I have a lot of it in my notes if you want to read through some of that. There's also some really good papers that you can find on DAFX that go through the derivation of the discrete Kirchhoff method. So I'm happy to connect you with those kinds of sources on it. So what we'll do is we'll be able to calculate some resistance for it. So we'll say R1 is equal to, if we have a digital system, we're going to have some sampling rate. So this could be like 48,000 samples per second. And as part of that, we have a relationship. If that's a sampling rate, number of samples per second, we have a sampling period, which is the time between samples, is 1 over Fs. So that's something we need to be able to use here. So sorry, this should be R1. R1 is equal to our sampling period divided by 2 multiplied by our capacitance. So this is how we're going to convert our system into something that basically just involves resistors and then current sources. Okay, so this is a resistor that we can substitute in place over here for how this would work. Okay, and then we're going to have this current that goes this direction like this. So that's some I, and I is going to flow this way here too. But then I gets split up and it goes down parallel paths. So if you remember, the way that this works is when we split that up, it's the sum of these two things. They're going this way. So I'm gonna have to talk about a new thing that I didn't hit before, but we have some current I that's going down through this whole thing, through our capacitor. It gets split up. Let's call this I2 and this one I3, okay? So I2 plus I3. Now, I3 is going to be the opposite of this current flowing back this opposite direction. So we have this current that we're saying is going this way, but our current source points the other way. So this is pushing a current back against the one that we have going up here. So we can make this substitution instead of being, we'll say I3 is equal to negative x1 at that sample number, okay? So we're going to substitute that in for this one over here, and then we'll have a thing that we want to write in terms of the Ohm's law for the voltage across this resistor, and the current going through it, and the resistance of it to substitute in over here. So we can say I2 is equal to the voltage across here, which will take voltage at our output over here is the same as the voltage across that resistance right there. So we can have V out over R1. So now these two things can be plugged in that we have, and we have this current is equal to V out over R1 minus X1 at that current time sample. Okay, so this describes the current that's flowing from this node here down to our ground, like this, and we'll use that as part of our analysis where we have this node over here from V in, and we can write the current going this way has to be equal to the current going this way. So we'll have V in minus V out over R2 is equal to V out over R1 minus X1 of N. And if we rearrange this, we'll solve for V out as a function of V in and X1, which will put it into more of a similar kind of circuit or digital filter sort of form. So let's move V in or X in over to the other side and V out over to the other side. So we have V in over R2 plus X1 for that sample number equals V out of 1 over R1 plus 1 over R2. Let's call this just some gain. It's just some gain. It's 1 over the resistor 1 over the resistor. So this is equal to V out times G, like this. So now we can divide G over on the other side, and we have V in over G times R2 plus X1 of N divided by G equals V out. Okay, so this looks hopefully more like a form of a digital filter that you're comfortable with. So maybe if I write it in this form, where we'll say V out is our Y, that's our sample we want to calculate at the current time like this, and V in is our X, our input that we want to calculate. So this is going to be, 1 over G times R2 times X at that current sample, plus our delayed sample is a way to think about it, our state, X of 1 times 1 over G, like this. So this is a coefficient that we can calculate and multiply by this sample here, and this is another coefficient that we can calculate and multiply by this state in the past. Now, the thing we have to be careful about here is how we update the state from one sample to the next one, because it's not a simple delay like it would be where you take X in and apply it and save it as X of 1. There's a specific state update equation that's used as part of the decay method, where what happens is you calculate the next sample, X of 1 n plus 1. So the sample that's going to be used for the next loop of your processing is equal to 2 divided by the resistor that belongs to that capacitor. So you use that one as just a rule for this for now. 2 divided by R1 times the voltage across the capacitor, like this. So that's right now, that's V out. We've already calculated V out in terms of our code. And then you do minus X1 at the current state. So this is how we can update our current source that we use as part of the substitution for the capacitor on this. And so our steps basically for our algorithm would be calculate these coefficients ahead of time, maybe as part of like some update samples thing, or update parameters function, and then calculate your output for a current sample. And then once you have this value, you can plug it in and use it as part of your update over here. Now it'll be slightly more complicated in other circuits for how you use this or how you come up with this voltage, but the concept is the same, and this is always going to be the form of the state update equation like this. So the resistor that you've substituted for it, 2 divided by that thing, and then you subtract off the current state for it like this. So hopefully that gives you like a basic way to take this type of resistor and capacitor filter and turn it into something that could be, you know, a few lines of code in a plugin that perform the filtering based off of real component values of a resistor and a capacitor like that. So there's one more concept that I need to introduce before we just jump into the tube screamer circuit, and that's the idea of a potentiometer. So let me just write it on here rather than go back through some of my notes. Potentiometer is a variable resistor. So this is how we can have parameterized control of our circuit, right? You have a knob on the pedal that you twist the knob that is controlling this variable resistor that's part of the actual circuit. And so we need a way to be able to include this in our circuits that we're going to analyze. So a potentiometer, in terms of a schematic symbol, ends up looking like this. And so it's kind of a weird thing where you have a resistor that has, you know, some terminals as part of it, but then you have this third terminal that ends up belonging to this potentiometer as well. So the easiest way to deal with potentiometers in a circuit is to split them up and give them 3 terminals, but actually 2 resistors. So we'll have a resistor like this and another resistor like this. And this arrow that comes in is splitting up this combined resistance into 2 different resistors. So this is R, and we'll have R1 and we'll have R2. And so R is equal to the combination of these things, R1 plus R2. Now, what we'll do is we'll have this wiper that basically changes the resistance of R1 and R2 in a complementary way. So we'll have like R1 is equal to some value of our potentiometer multiplied by R, and R2 is equal to 1 minus our potentiometer times R. That's our original total combined resistance for the potentiometer. And we'll say that our wiper can only go between, take on values that go from 0 to 1. Okay, so this is how, if we have a variable knob in our plugin, we can incorporate that as, change the value of that knob on a normalized scale from 0 to 1 and include it into a schematic by splitting up the resistors in these different ways. And then all the other rules that we've been looking at for nodal analysis and things for the circuit analysis will apply for what we're trying to analyze. So that's the idea of a potentiometer. There are some cases when we're looking at like our tube screamer where we're not going to be able to go all the way down to 0, and even in some cases not all the way up to 1, because like this could result in us dividing by 0. So if we have like some value that's 1 over R1, we don't want to actually divide by 0 here on it. So that would be a problem. So sometimes what we end up doing is like having a very, very, very small value of our potentiometer that we end up using. So just some stuff to warn you about as we get into the tube screamer on this. This is also just assuming that this is a linear potentiometer, but there's also other kinds that are like logarithmic, skew and things like that. So you could change these functions to be other things too, to have that work. So let's just use what we've got so far and jump in and start talking about our tube screamer schematic. So we're going to focus on the one right now for the tone and volume section right here. So we go back. Nice thing about the Electro Smash is it has these things broken up into different sections that we can look at. So the one we're interested in first is this section right here for the tone and volume control. So what you can see is, I'll talk through some of these things, is we have resistors, capacitors, an op-amp, and potentiometers. Those are all components that we have discussed, and we have these different nodes that we can go through and label. We have our input voltage node over here. We have our output voltage node that's taken off of this potentiometer. We have this op-amp in the middle with a positive terminal and negative terminal. And we have ground. And then we have some other things that I need to explain how we're going to deal with them in our model. So for instance, there is a terminal or a node right here that's labeled 4.5 volts that is then connected to our positive terminal going into our op-amp. So what's happening in this pedal itself is our op-amp is set up to have a range that goes from 0 volts up to 9 volts. So this 4.5 volts as part of the circuit performs a DC offset to essentially take our input signal that was oscillating around 0 and move it up so that it's oscillating around 4.5 volts. That's because we're going to supply a battery to this op-amp, and so that's the range that it wants to go over. Well, what we're going to do is just ignore that, for better or for worse. We don't have to, but we could. We can ignore it, and it works out okay for the tone section on it. We'll just ignore that there's a DC offset, and we'll assume that our op-amp is just, there's no clipping that's going to go from 0 to 9 volts. We're just going to allow it to have whatever range it needs to have on it, and include going down to negative voltage and then positive voltage on it. So that's a simplification that will make our lives a lot easier on it. And I think that's an acceptable one to do. Also the weird thing that comes up in this circuit that's, we picked this one. I picked this one because it's kind of a interesting one that a lot of people are familiar with. But there's this kind of uncommon thing where we have a potentiometer that goes across our negative and positive terminals of our op-amp. So in almost all circuits that have an op-amp, you will very rarely ever see a component or anything that connects outside of the op-amp, the negative to positive terminals. And that is done so that we can assume that it's behaving in an ideal way, and it's much easier to work with when you don't have something that is connecting these two terminals external to the op-amp. What we want to be able to do is still assume that we have an ideal op-amp, and so there's no current that's flowing between the negative and positive terminals of the op-amp. And so in order to kind of still use this potentiometer as our main tone control, what we're going to do is split this up and assume that there are actually two different paths, one that belongs to this part from our input going down to ground, and then we'll assume that there's another path going from our negative terminal over here up to our ground, and there's no actual connection between these two things. Tone control is going to adjust these things together. I think that in this circuit, in the tube screamer, it's kind of a clever way to have one knob that controls all these different things. But for us, in our model, that makes it kind of ugly. So you can sort of see in Electro Smash how they have decided to deal with this, where you have, if these potentiometers are basically like a point where you have the wire that goes between these two resistors. In my example that I gave you, what's happening here is as you turn the potentiometer down, this resistor goes to 0, and this resistor takes all of our total potentiometer resistance. Or it can go the other way, where this wire goes up here, and this resistance goes to 0, and then all this goes to here. So that's the extreme case when you basically have this, you're able to break it apart, and you have this flow of current that goes from our input through this path down this capacitor right here, C6, and then through R8 down here. But then we don't have anything going through the path on this top branch. But then the other case, when you turn the potentiometer the entire other direction, then we're not going to have current that is able to flow that way. And we just have the current flowing down through this path, up through this capacitor, up through this potentiometer. So what I've done in my model, and I think that it, just from testing it, it works out okay, is I end up combining these two things together, where I have a path for the input voltage to go down this way to ground, but then I also have a path for it to go this way through these things, components too. So I put both of them in and try and use them. So I think that it works out okay, and we end up getting this kind of frequency response in the model that I came up with by doing it this way. I don't know, it's an individual choice that I made. If people have other ideas for the better way to do it, have at it. But that's what I am going to demonstrate, at least, for how this is going to work. Okay, in the interest of time, what I'm going to do, rather than write out all the notes by hand, is I'm going to take you through the analysis of the circuit by the notes that I've already written out, because it will take me about half the time to be able to cover them. So if you are following along with the notes, let's jump ahead to the end of this first set. Here, so we can talk through it. This is the schematic for how it's written out in Electrosmash, but here's the model that I actually end up using down here. So I can zoom in on that. So you can see where I'm making the substitutions for these different currents, or capacitors, with R1 and X1, and R2 and X2. So this branch up here, I borrow part of the resistance from the potentiometer, and then I have a capacitor and I have a resistor. And so this is the potentiometer that's split, and then it goes into the capacitor, and then it goes into another resistor. And I duplicate this, but I have the opposite wiper value up here. When we go the other direction, my potentiometer I've just called alpha, and it goes through that potentiometer, then goes through a capacitor, and then goes through the resistor down here on it. And so that's how I'm dealing with that particular potentiometer. And then I made a substitution over here for our capacitor. Technically, this capacitor is supposed to handle the DC blocking of this 4.5 volts offset, but you know, we're not using that 4.5 volts, but we'll leave the capacitor in there. Okay, so this is a complicated circuit to try and analyze, especially based on what we've covered very quickly. So how I've labeled some of these nodes is I call this node over here, we have Vn, I call this node over here Vx, is everything happening going into this positive terminal. And then also Vx is connected over here for this negative terminal, okay? And then I have another terminal, or node that I've called over here Vy, and then we have some stuff for our output voltage that I have an output branch that I look at down here. Okay, so my idea for how I'm going to analyze this circuit is to break it up into different sections. The first section to look at is this one right here, where we want to write Vx as a function of Vn, okay? And then if we can do that, we'll have Vx that we can assume is the same up here on this negative terminal. And then we'll want to have Vx, and there's some voltage that then we can measure from Vx down to ground over here. And then we'll want to connect Vx over to Vy here, and then Vy to our output. So this top part up here is going to be another analysis that we do. And then our whole output is going to be a third one. And we'll connect them by these nodes that surround the op amp. So basically we'll have some current that we connect for this part of the circuit, and then, or a voltage that then we connect to this part of the circuit, and then lastly this one over here. Okay, so the first thing that I want to do in this is write the voltage here, Vx, based on its current, because we're going to have some current that goes through this resistor here at the beginning, Vi minus Vx over R6. Then we're going to have a current that goes through this capacitor, that'll be Vx and these things, and we'll have a current that goes through this one, right? Our one current here gets split into this path, and then it gets split into this path. So let's focus on this path first, because that's the more complicated one. Okay, so we'll start with this sub-circuit where we have this voltage Vx here that goes through some potentiometer. It goes through this capacitor, which is R2 and X2, and then goes through R5. So first thing to note is that this is a voltage divider kind of circuit. So we have Vx that gets divided up into, or split into V across the potentiometer, our voltage across this potentiometer, the voltage across this resistor, and the voltage across this resistor. So VR1, VR5, and VP1. We know that the current that's going down this path has to be the same through each one of those stages. So this current that goes through this potentiometer has to be equal to the current going through this resistor and this capacitor model that we have. So what we'll do is find each voltage as a function of P1 and then plug that in to the whole equation, and we'll have something that then we can just write as a function of Vx. So we can equate these two parts. We have VR1 over R5 is equal to VP1 over P1. Let's solve for VR5 that will plug in up here to this VR5. So we've solved that one. Then we can do it with the next step, VR2 over R2 minus X1. We'll go through that. And we have VR2 as now a function of VP1. So we'll take VR2 from right here and we'll plug it in up here. I guess it should be, why did I call it VR2? This one right here should be VR2, not VR1. Sorry about that. So we plug all those things in. We have Vx now as a function of these things that just depend on VP1. Okay, so we solve for VP1 and we'll write this gain along the way of gain of 2, or this G2 right here, that then we divide off only to the other side, and we now have VP1 equals Vx minus R2 over X2, or multiplied by X2 over G2. And now we can, now that we have VP1, we can plug that back in for our current and divide it by P1. And now we have our current that goes through this whole path as a function of the voltage and our state and nothing else. So that's an important form for us to get and save that we can then use later on. Okay, so just went through some algebra steps to get to that point, but we'll save that as the current going down this path right here to use later on. Okay, I do a similar thing over here with Vx going through this path, and you get a thing that we need to save is G3 on this, and this is the end result that we have for the same thing. They're identical, you know, it's identical schematic just with different values on it. Okay, then there's an output branch for us to look at. So this is where we're going to go through a capacitor, we're going to go through a resistor, and then we're going to go through the potentiometer. So that is this section right here, the capacitor and the resistor and the potentiometer. Sorry about that. So we know that the current going through all these components has to be equal to each other. So we have to write everything as a function of V out, because ultimately we want this as a relationship between V in and V out through this whole entire thing. So I'll just define a few other nodes in here that we have VB, we have VA, and then we have VY. So I promise you, if we do a very similar kind of substitution from stuff we were doing in the previous step, we can save this one for later. This VY is equal to V out. So we're going to want to replace VY with V out that we have here as a way to eliminate VY from our whole equation on this. So we have a bunch of these things now laid out with Vx for the different parts, and we also have a Vy. Now we need to go through and connect our branches together. So let's start at our beginning and say that we have, I guess my next step is I'm connecting our node Vx to Vy in this way. So there's a node here that we know Vx, we know Vy, and so there's a current that's going across this node here over to Vy through this resistor, and that has to be equal to everything that's going back down this way. So we have a current going out of this node and the current going out of this node the other way. I guess they have to be going into the same. This one's going into the node from VY over to VX and from VX down to ground. So this is how we connect VY and VX together. A bunch more algebra. Sorry to be skipping over it, but it's probably also not the most interesting thing to cover. Probably like to get to some code here soon. So now we have a way of connecting our output, V out, over to VX over here. That depends on our states. I think there should probably be an X3 right here. That's missing. So sorry about that typo in the notes. Okay, now we're ready to handle the currents going into our beginning of our circuit. So we have our current from V in over to Vx, plus this one going down this direction and this one going down this direction. So I write those out here. Vi equals Vx over R6 equals Vx over R1 minus X1. So that's our capacitor. Then we have that whole branch of stuff that we calculated before that represents the current going through all those different things. So what I do is just some algebra to isolate Vx. So then we have this just as a function of Vi and X1 and X2. And we have this other Vx from before that we calculated up here. And we can set those two things equal to each other. So we set those two things equal to each other. And we have now eliminated Vx and Vy. We just have a function of V in and V out, and X1, X2, X3, and X4. So those are our capacitor states. We rearrange this and solve for V out. Now we have it in this nice form, looking more and more like an equation that we can use for a digital filter. And I've just defined some coefficients that we can use. That this one I'll just call B0. This one over here I'll call B1. This one I'll call B2, B3, and B4. So these are ones that we'll want to calculate actually in our plugin here that we'll work on in just about 2 minutes. So the last thing is, now that we have V in as a function of V out, we need to update our states, okay? So this is where we have the voltage across the different capacitors that we need to worry about. So X1 is this, the voltage across it is Vx. So we're looking at this capacitor right here. The voltage that goes across it is Vx. This one's tricky because we have to have a voltage that goes from this node down to this node. And that's the one that we need to use in it. I guess for the sake of time, I can just skip ahead and say that we have Vx1 that we are going to calculate with Vx for it. We have X2 is this one right here. We have X3 for it, and X4. So those are our states that we need to update. If you want to double check my math on it, you can, or work out the math by hand to see for yourself. But that's what we're going to plug into our plugin. So those are our equations. Let's switch over to JUCE now and start working on the tone section and see if we can get that functioning before we take our next break. So I'm going to go over now and pull up the JUCE one here, the TS pedal. Let's go ahead and launch that in Xcode, or if you're using Visual Studio, go for that. I think I had it in a pretty good spot, but you might need to make a few changes to things. I don't know if it was exactly right. So let's take a look around of how we're going to set this up. So we have the typical class that we use for the editor and the processor that come with the JUCE plugin. I have one that actually one of my students created for the graphics of the thing so that it sort of looks like a Tube Screamer guitar pedal. We're not going to really get into that one, but it's there if you want to check it out and see some stuff with that. So the pedal component is the one that handles the graphics that we're going to use. And basically it's set up so that we have these variables in our plugin processor that are public variables, just as a simple way that these values right here are set up to automatically get updated by the values in logic. So, or the knobs of the plugin that we have set up already. So when we twist this knob, it will update the value that's for the drive value in our the public variable in our plugin processor. Same thing with the tone and output value. So we can use those variables and pass them into our classes that we're using for the processing as a way to and know that their values are there and ready to work. So over here in our plugin processor, we are going to want to pass in like the sampling rate and stuff to our classes. So I guess I should mention, I've got these ones prepared ahead of time that are kind of bare bones skeleton that we'll want to use, where we have, you know, process sample, prepare and set the knobs for this, and then some coefficients that we're going through and calculating on these as well. And then we're going to add in a bunch of stuff down here for the different variables. And then over here in our plugin processor, we'll prepare. We will, in our process block, we'll pass the samples in, or each sample at a time, and then get the samples out and be able to do the processing that way. So let's go ahead and just clean some of this stuff up so that we can get the basic functionality in place for how this is going to work. We can call, let's see, we should create an instance of our tone section here. So let's do include TS tone like this. Now we can create an instance of it down here. Like this. I want to make sure I'm following along with my notes. I don't miss anything on this. Okay. So I'm just going to call this instance of it tone. Okay. Like this. So now in our plugin processor, we'll go to our prepare to play and we'll say that we're going to have tone here. And I think I called it prepare. And we'll want to set our sampling rate in here. So we'll call that method for it. So pass in our sample rate, get things initialized. And then over in our TS tone, let's make sure that we have, okay, this is already set up where we will update our sampling rate and then update our coefficients down below. So that one should be good to go. Then in our plugin processor, when we actually want to do the process block, what I'm going to have us do is just go one sample at a time rather than pass in the whole buffer. If you want to program it that way, you can do that too. But let's do that where we will go through the channels, and then we'll go through a loop for int n equals 0, n less than buffer get num samples plus n. So this will just write a loop that we can go through each one of the samples of our buffer. Let's get a float from that. We'll just call x, which is buffer dot get right pointer for the channel number for the index of the sample n here. And now this is the thing that we want to pass in to our effect and have it do the processing. So we could have like float y here is tone dot process sample, and we pass in the x, and we pass in the channel number, and that will do a step of processing for us to use. Oops, I need to call that channel. And now we'll store this to our right pointer again, buffer dot get right pointer for that channel, and that sample equals y. Okay, this isn't the most efficient way to write the code, but I think it's hopefully intuitive. Okay, so a few more things that we can use here while we're in the process section is, sorry, we have it here. We have this effect on. So let's write a conditional that we can use. I'm not doing any smoothing on this, but it will at least trigger our effect being on and off that we can test that it's going to work. So let's write it like this, where we have if effect is on, we'll do this step, and else we will just do buffer dot this thing equals X. So no processing. We'll just pass the input that comes off of the buffer to the output again. Okay, and then we'll also want to update our parameter. So I have a method set up to do that. Set the knobs here, which there's two knobs. There's the tone knob and the output knob. So we have those values to work with here, the tone knob and the output one. So let's put those in. We'll do tone dot set knobs. And I've already forgotten the name of the one I called it, tone value and output value. Okay, so this will pass the values over here to this method, and we'll want to do some stuff with that. Let's go ahead and start to put in our values of all our circuit components, and then from the circuit, and then start to use them. So let me find this. We'll start out in the header and just define a bunch of these things. So here, we're gonna have to put in a bunch of them. If you wanna copy this from the one that I've already set up, go ahead and do that. But we have a float for our capacitor is 22 microfarads or 0.22 microfarads. That can be used to create this resistor R1, which is TS over here, 2 times C1. And we'll do a similar thing for some of our other capacitors that we have. So there's a total of 4 of them. Okay, so we have C2 and R2, but this one has a value of 22 as well, 0.22. This one is the third one. So this one, that's good. And our last one is different. It's 1 microfarad, that should be C4, like this. So, and this is an equation that comes from the decay method for how you can substitute the resistor. Okay, then we have the values that you can just read off of the schematic for the different resistors. I've called this one R5 is 220 ohms. R6 is 1,000. R7 is 1,000. R8 also 1,000. Or no, that's 220. Okay, now we have R9, 1,000. Now we get our potentiometers that we're going to use. Initially, I'm going to just have this potentiometer for our output, and we'll set it to a value of 1. Maybe, yeah, that's fine. Value of 1. R10 is going to be 100 kilo ohms. times, this is where we do that wiper of 1 minus our potentiometer for our output. And then we'll have a complementary one, which is R11, equals 100 times our potentiometer for our output. Then we have a potentiometer for our tone, is start at 0.5 and have what I've called P1 here equals 20,000 times pot for the tone, and P2 is 20,000 times 1 minus tone pot. And then there are these grouped resistances that I've calculated, or these G values that if you look at the notes, you'll find them in there. But these are just there to make our lives easier. Let me put these in. Just substitutions of stuff. 1 plus R2 divided by P1 plus R5 divided by P1. Float G2, 3 equals 1 plus R3 divided by P2 plus R8 divided by P2. Yes, float Gx is 1 plus R7 divided by G3 times P2. Float Gz 1 R1 plus 1 divided by R6. So once I type these in once, it'll be easy to copy and paste wherever else we need to use them. So this is where I would encourage you to find the plugin that's already been done and make use of that rather than typing all this stuff in. Okay, we have our states. Didn't have a G1. This should be R1. So our states, we're going to have X1. And we want this to actually have two states, one for the left channel and one for the right channel. So there's a total of 4 of them. And each one, you have to have a different one in memory for the left and the right. And then I have these filter coefficients that I've just called B0, Gx divided by Go, R6, and Gz. This would be 3, 4. Okay, so that's all we need to define here initially. Hopefully I typed everything in Okay. We'll want to use some of this stuff also in where we're updating our coefficients. Whenever our knob changes, our potentiometer, things that depend on the potentiometer need to get recalculated on that. So let's switch over to that part and see what we need to have for that. So anything that depends, just copy all this, and then I'll maybe exclude some stuff, delete it. We don't need. So anything that depends on our sampling rate, we might need to get updated. Over here, update our coefficients. Okay, so we need, these don't need to change. This doesn't need to change. We don't want to overwrite our pot. That will get set up above for each of those things. And we don't want to redefine all these as floats. So my copy and paste idea maybe wasn't the best. We don't want to change the states, so let's get rid of that. But we will recalculate these. Okay, so I think we're in a much better shape. The one thing we need to do is control how we're going to change the knobs right here. So let's program that and say we have some tone knob coming in where if let's, I guess for now, say our pot tone is equal to, we don't want our tone knob to go all the way down to 0. That would actually cause a problem for it. So we'll make it some really, really small resistance plus six. And we don't want it to go all the way up to 1 either. So we will use this equation for it. Our output knob, it actually ends up working out okay if the output does go all the way up to 1, but we don't want it to go all the way down to 0. So similar thing. Times our output knob on this. Update those things, and then we want to call and update coefficients. Now, this is probably there's much better ways to do this if this were a commercial product. So, we don't have time to get into all those. I think in the example that I give, I have a conditional to check, and you only update the coefficients if one of these knob values have changed. But for now, we need to get on to writing our process sample one up here, where we have our voltage going in, and you want to have some voltage going out. So this is where we use some of the stuff from before. I'm going to create a new floating variable called voltage for our output. We've done these once, calculate them already, B0, and our voltage times our input, plus B1 times X1, plus B2 times X2, plus B3 times X3, plus B4 times X4. Okay, then for our state updates that we need, I have a variable that I calculate called Vx, which is V1 divided by R6 times GZ, and X1 divided by GZ plus X2 times R2 divided by G2 GZ times P1. And now we can calculate our state updates of 2 divided by R1 times Vx minus X1. X2 is 2 divided by R2 times Vx divided by GR plus X2 times V1 R5 divided by GR minus X2 X3 Vx. X4 okay, and we're going to return V out. Okay, I'm missing something here. Maybe I have not defined something in tone. B0, B1, B2, B3. We need to index based on X1 of that channel. And again, there's better ways that you could code this to make it more efficient, but just need to get something going. Okay. If I haven't forgotten anything, which it's highly likely that I have, we should be able now to make sure we have this set up. We're processing the sample in there. Let's build it, close out of logic, and see if we can get this going. About to take another quick break. If necessary, I'll troubleshoot this over break, or maybe someone's already posted in the chat if I've got any typos or things in there. I know that there's a lot to connect where I skimmed over in the algebra with what we have in the code. But if you have more time to dig into it, please have at it. I'll also mention while this is building, I have taped a 16-hour version of this workshop previously. If you're interested in it, find me on social media or find me on Discord after, and I'd be happy to set you up with the more long-form version of this workshop where I go into and spend the time to go through all the algebra of the different parts and don't just skim over things and plug and chug. So if you're interested in that, let me know, connect with me, and I will make sure to get you set up with more detailed explanation. If you're new to circuit analysis, I'm sure there was tons of stuff that I skipped over that would be helpful for you. So see if I just have a okay, so at this point, we are only really using the tone and the output. Made sure that here we set those things. So I guess our only check is just to play it and see what happens. It looks like we have something that went unstable. So let me stop here so we don't waste anybody's time. Let's take a break, get back together in about 5 minutes, and let me see if I can track down where our issue might be in the code. So, hey everyone, so I'm ready to get started again, just in the interest of time and trying to make sure that we have stuff working. I'm going to switch over to the branch that I already prepared previously, and I encourage those of you that are trying to follow along to do the same. So I have a branch that that is called the completed plugin. And so just to make sure that we have stuff that's going to be working, I have switched over to that branch. And I'm going to be working off that one and trying to get through what we can. So there was a couple things that came up in the chat that I think are probably important based on what we have in here. So I pull up, we have in the tone section. So I just implemented a mono version in the completed plugin. So just be careful of that. If it's the case that you want to do stereo, you would just have to pass in that channel. I forgot to do that in my initial demo when I was working on it. But it basically just comes down to whether you make these into arrays or whether you just have them processed as individual states. So just be aware of that. I think that this one will end up working if you build it. So that one shouldn't have the same bugs that were created before. So that's one thing to warn you about. And I guess in that case, what we can do is work off of the next section of the tube screamer that we want to work on and talk about nonlinear modeling that we want to do. So let me pull up this other set of notes. I'm going to do some stuff by hand again because I think that it's important. I guess I didn't copy that one into the repository. So let me do this. Go back to sorry about that. Okay, so if we look at the electrosmash circuit for this last part that we want to model, I can tell you it's not nearly as many steps as the tone section. So that's the good part that we need to do. But we are going to encounter this new type of component that we haven't come across before, which is a diode, which has a nonlinear relationship between the voltage and the current that goes through it. And in fact, we have a pair of diodes that's going to do the saturation or the distortion as part of this clipping section. So we need to know how to deal with a diode. So let me do some notes on this, and then we'll get to the modeling aspect of it. So this. So a diode has a schematic symbol that looks like this. And the basic idea of a diode is it's going to allow our signal to flow through when it, or stop the signal from flowing through when it's either positive or negative. So it acts like a full wave rectifier, essentially, is the basic idea, where things that are negative end up getting clipped off and things that are positive end up getting clipped off. And depending on the configuration that we end up having, it can either clip off the positive parts or the negative parts and do that kind of thing. This is kind of an ideal case of the diode and how it ends up working if we were to connect it with like a resistor and look at the behavior like that. Other ways to think about a diode is that if we look at like a plot between the relationship between voltage and current for a simple resistor, whatever that resistance value is, we have this linear relationship, straight line here, where V equals IR, or V over R equals I. So as we increase the voltage, we're going to increase the current by some proportional amount right here. When it comes to a diode, we have a different sort of relationship. We will have no current that flows through when we have a negative voltage. So no current. That means we have an open circuit. And then when we go to a positive voltage, in an ideal case, we have a short. Okay. In reality, this isn't actually how a diode ends up functioning. we have more of a plot that ends up looking like this. We have maybe a little bit of current that can sneak through down there. And then a curve that ends up looking more like this. It does reach a point where the current, it does end up taking off and going up very, very quickly for higher and higher voltages. But there's this region around here, around 0, where it doesn't have this instantaneous, really, really high steep slope. Now, for different types of diodes that we come across, we're talking about semiconductor diodes here. Where this really starts to take off is going to depend on the type of material that's used for the diode. So you may have heard of like silicon diodes, or common ones, or like guitar pedals. It was kind of vintage to have germanium diodes like this. This point where it really takes off kind of depends on the material that's used. And so this is usually somewhere around like 0.7 volts. This is voltage and this is current here. Or if this is germanium, maybe it's closer to like 0.3, okay? So this is the type of look to the relationship between voltage and current that we have for the diode. There's an equation that we can use called the Shockley diode equation, where we have the current here is equal to some constant variables that we're going to set as part of it. And then there's like a voltage that goes across the diode. So there's the current ID that goes through the diode, and there's a voltage that goes across the diode like this. So our equation between the current going through it and the voltage across it is the saturation current. That's a thing here called saturation current. This will depend on the type of material we use. And then we'll have this times E raised to the power of the voltage across the diode divided by this quality factor variable for like the purity of the diode, Greek letter eta. And then there's a thermal voltage that depends on like the temperature of things for the diode. And these are ones that we can adjust, but there's common ones that we will also find. And this whole thing minus 1 will give us our relationship now between voltage and current. So we have this nonlinear part of it with E raised to the power of, this stuff that we have to deal with. Eta is this quality, and VT is thermal voltage. So all these things are part of the Shockley diode equation, and I have them listed out in my notes for the actual values that we could use for them down here. So for silicon, we're going to be somewhere in the range of 10 to the minus 12 or 10 to the minus 15th. For germanium, it's going to be 10 to the minus 6th for that value. Silicon, some of the times the doping that's done for it can be maybe more pure, so we could use like a quality factor here of 1, but there's usually somewhere in the range of like 1 to 2. This is going to change in some ways like the slope of this line that ends up happening. So that's one that we can do. The thermal voltage is somewhere around here. It's like 0.20 or 0.025 or something like that. I have it in the plugin already defined, but those are going to be constants that we set and we can just use as part of this. So what ends up happening when we try and include this diode in some of our circuits that we're trying to analyze? So a basic one that we could work off of is one here where we have a voltage source like this, and we have a resistor, and we have the diode here like this, and we have V in, we have V out. We'll say that V out is equal to VD, the voltage that's going across the diode, and we have some resistor right here that we want to use. So we'll do this nodal analysis where we have the current going this direction is equal to the current going this direction, which is ID, like this, and see what happens when we start to plug some of these things in. So we'll do V in minus V out over R is equal to, now we plug in our Shockley diode equation for ID right here, which is IS E to the VD is equal to V out. So we can just write that, plug it in right here. Eta VT minus 1. Okay. And if this were a linear circuit, everything we've done up to this point, what we tried to do is rearrange it using algebra till we got to the point where we had V out as a function of V in. And that was always the goal. But we run into a challenge here that comes up when we have this nonlinear part of the equation. So we could do something like try and take the log of this side and the log of this side, but we still have that nonlinear part that we're stuck with and we can't get rid of as a way to isolate V out on each side. So this is a special type of equation that we've got to deal with in a different way than all the ones we've dealt with up to this point. So in mathematics, the name of this type of equation is called an implicit equation. So for us, there's not, the way to think about it is we can't isolate, cannot isolate V out as a function of V in the same way we could before. The way that that's described in math is that there's no analytic solution to it. So the other type of equations that we've been used up to this point are called explicit equations. That's what we normally think of. Y equals mx plus b. You can rearrange stuff and get it into a form where you're able to calculate stuff that way. So implicit equations, we can't come up with an analytic solution this way. What we have to do is come up with a numerical solution. So use numerical solution. Okay. So the way to think about this is we're doing a guess and check process. Guess and check. So where we basically try out values for V out, and if they end up causing this to be equal to each other, then we're saying, great, that's the value. But we could also plug in a value of V out and say, all right, what we get for this side of the equation does not equal what we get for this side of the equation. So that must not be the correct value of V out. That is the solution for this relationship between these things, okay? So graphically, the way to think about this is if we had some function that was going through something like this, and maybe we have some guess of what we think it's going to be right here, that might not be the actual value, but what we need to do is come up with a way to get this so that we find what's called the root of it. Well, technically, the best way to do this is we actually rearrange this so that we solve it for 0. So now we can find the root of it this way. So let's rearrange this onto the other side. We have 0 equals IS E V out over eta VT minus 1. And then we'll have a positive V out over R minus V in over R. Okay, so now we have this in a form where V in is going to be known. Everything is going to be known except for V out. We can't isolate it. So we need to guess and check some values for V out until we get this whole confusing mathematical function to be equal to 0. We could plug in something to begin with and it's not equal to 0. And then we say, well, let's try another value. We could try and go up and we could say, well, that actually got worse. Or we could try and go down and maybe we find that got better. So let's keep going down until we get to this point down here. So this is the concept of doing a numerical solution, of going through and trying values until we get one that is acceptable, or maybe within some tolerance that we say, if we're close enough, we're good. Let's just go with that. So the one that I described initially here of just slightly moving things down, that's very slow. It would take many, 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 many guesses and checks to probably find the one that works. And so what I'm going to show you how to do is a faster method that's called the Newton method or the Newton-Raphson method. Where in fewer iterations, our goal is to hopefully get down here and find this point that's our solution to this thing. And we'll use the Newton-Raphson method in our model to deal with the diodes that are part of our equation. So one of the things that I was discussing is this idea of going up or going down. And In calculus, this concept is we want to move along the slope or look at the slope, where we could say if the slope is positive, then we want to move in this direction. If the slope is negative, we want to move in the other direction. And so there's this idea of this derivative that we can have is the slope at this particular point where we're at in the beginning. And with most of the equations that we come up with for circuits, we're able to find the derivative at this particular guess that we begin with and use a derivative to our advantage. And that's what the Newton-Raphson method is all about. Hopefully people that are attending here are familiar with the concept of the derivative. If not, that's gonna have to just take my word for it for now. So let me draw for you what this method is all about, the Newton-Raphson method. Is let's say we have this nonlinear function that ends up looking like this, and we want to find this point right here, and we're starting from this point right here. So here's what we're going to work with. We have some guess, let's call this V out, okay? And then we have the value of that is going to be the function at the point for V out. This is our nonlinear function that we get a value for it when we plug in V out for it. And then we also know the slope of it right here. So the slope is going to be equal to the derivative. So I'll write it F with this flag, the derivative of V out. So we have F of V out is equal to this IS E to the V out eta VT minus 1 plus V out over R minus V in over R. If we take the derivative of this, what ends up happening is we have these separate terms to deal with. There's going to be this eta VT that comes out front, IS divided by eta VT. Then we just have E to the V out over eta VT. So that's one term plus 1 over R. Okay, so this is our slope. So what we're going to do in an iterative process is take what we know at any given point in time, which is our V out value. We plug it in, we get a value for the function over here, and then we get a value for the slope. And we can use those things to help us find a new point where we're going to jump way ahead to something that's hopefully closer and find a new point where this is V out for our first guess. So guess 1. Then we'll move out and we'll try this as our new V out value for our guess 2. Okay. And then we'll be able to get some new things here, a new slope, and eventually we'll be able to move down until we get within some range and we say, okay, we're good enough. You know, we've moved V out closer and closer. Maybe that only took 3 iterations or 4 iterations to make that happen. So let's think about why this works for us to find these things. So let's say we had some points in a coordinate system. So we have, maybe this is x1 and we have x2 that this is the thing we're trying to go for, right? And we start out with this point here and we'll call this y1, okay? The y value that we're gonna end up with down here in our guess, we'll say that it's gonna be equal to 0, okay? Because of the slope. So if this is what we have, these things in place, our slope here is equal to the change in y over the change in x. So y1 minus y2 over x1 minus x2. Okay, our slope, this is actually known. This is this value, V out, and we have y1, which is this f of V out minus 0 over here, over x1, that's our initial guess, V out for guess 1, minus V out for guess 2. Okay, so if we start to rearrange this, this is the thing that's unknown. We don't know this one. So let's move this over to the other side and move this down here below. We'll have V out of 1 minus V out of 2 equals F V out over the derivative of V out like this. Now let's do it where we solve for this term over here, our V out. Let's move it over to the other side. You have V out of 1 minus this should not be the derivative. You have the function divided by this one here, V out, is equal to our next guess. So here is the Newton's form for doing the update to your numerical solver. You take your current guess and you subtract off its value in the nonlinear function divided by the derivative of this function to get your next guess. So then we could take this one and we could use this as our next guess, and we could subtract off, we could plug this one into our V out and our function here for V out and our derivative for V out, and we could then incrementally move on by keep plugging it in to new places until we find that continually update until f of V out is essentially 0 or less than some threshold. We say, all right, that's close enough for rock and roll. We're down very close to 0, and let's be done with trying to find this value, and let's move on to more things. So this is exactly how this ends up working. If it were the case, let's just write out the pseudocode for this one before we get to the tube screamer. So if these were the things that we had, like this, for it, we would steps. So the first thing we would do is initialize V out is something. It's our guess. Let's just initialize it to 0. Okay, and then we'll go through, a sample. We're going to have something in here where we're processing a sample of input. And our result of that is we want to find, by the end, find V out, like this, okay? So what we would do is initially calculate, I'll call something here the numerator, is equal to these things that we can plug in. So IS E V out over eta VT minus 1 plus V out over R minus Vn, and we check. Whatever our value of Vn is coming from our processing and our plugin, this should be over R. We find this and we check, is the numerator less than some threshold? Or really this needs to be some absolute value. So take the absolute value of this is within some range. Okay, if it is, then our V out is good. So, return V out. If it's not, what we need to do is go through the solver. So we would then find our denominator is equal to this thing, IS over eta VT, e to the V out of eta VT plus 1 over R, like this. We find this one, and now we need to figure out our new V out. So our V out is equal to our previous V out minus our numerator divided by our denominator. That's our Newton step. And then we calculate a new numerator in here. So same thing as up above. And then we do a loop. While this is not true, let's keep repeating these steps and changing our V out until we get something that's within this threshold. And if it is, now we're done. Let's leave the loop. And this is the value that we know solves this equation, this nonlinear equation, to give us the result of V out that we need that comes from V in, that satisfies what we need for that. So those are the steps. Now in practice, what ends up happening is we need to be careful about this, and maybe we don't want to do an infinite number of loops, and it's possible we can get stuck in here. So we might want to just have some iterations and say after 50 iterations or 10 iterations, let's stop and just move on and say we can't hold up our plugin from processing on and on and on. There's also a thing that I don't have time to explain in detail. It's in the notes, and I have it in the code called the damped Newton-Raphson method, which prevents, or is is there as a guardrail to hopefully prevent the numerical solver from going unstable, where you're actually getting further away from zero as you go through these steps. And that would be a problem if you keep getting further from zero rather than closer to zero. And there are some equations and certain signals that would come through here that could cause this to go unstable. And that's where there's this thing called the damped Newton-Raphson method. Look it up in my notes or papers that are on the subject, and you'll see, kind of the steps for how you would do it. You basically, when you find your numerator, you like recalculate it again and make sure that you're not getting larger, you're only getting smaller from it. Okay, so now I need to talk about how we're going to use this in the circuit for the tube screamer. So here's our circuit. We have, it's way more complicated than the example that I just gave you. We have resistors, capacitors, and we have diodes. We have potentiometer that we need to deal with. I forgot to mention one more thing about this before we jump into this, and that's for a pair of diodes, how we deal with a pair of diodes. So let me switch over and make some notes on that. So very quickly. Pair of diodes. So there's a common way that you'll find in lots of guitar pedals, especially where you have this kind of thing happening, where you have two diodes that are in opposite configuration, where the polarity on them actually matters a lot for it like this. And you could write out all the currents to go through each one of these separately, but there's a nonlinear equation that works if these two diodes are identical to each other, where you can write it as a single box or a single block for both, to model both diodes together as a single current ID through both of them, okay? In this case, our diode equation becomes 2is times the hyperbolic sine function of the voltage across them, VD, divided by eta VT, okay? And the derivative of that ends up being 2is over eta VT, sorry, this should be sine H, and this is cosine, hyperbolic cosine of VD over eta VT. So this is the one that we're going to end up using and substitute in for a single block of these diodes to be able to use. So that's a simplification that you can make only if you have these diodes being exactly identical to each other. Otherwise, you'd have to treat the currents separately. Okay, so here is our circuit for it. One of the things that I'm going to do to simplify it for us is, again, we have this DC offset, and I'm going to ignore that and say we're not going to have any DC offset to worry about, or we're going to allow our signal to go positive and negative. And another thing is, because of that, we have a voltage that's coming in, and we have these components that we encounter, some capacitor, some resistor here. And if we just treat this circuit in isolation, what happens is there's no current that's allowed to be drawn to go into the op amp over here. So I'm going to ignore these components right here and just say we have Vin over here at the positive terminal of the op amp, and we'll just ignore these for now. Technically, they're there to help with the other sections of the circuit to make sure there's like no DC offset that's getting blocked by this one. So if you're trying to model the whole thing, you might want to take those things into account. So here's our positive terminal, and that means that our Vin is going to the positive terminal, and it's also going in to over here for our negative terminal. So in effect, we have our output going through this section straight to our Vin, and our Vin then is going across this capacitor and going across this resistor right here, okay? So we have those things occurring, and that can make it a simplified circuit is going to end up looking like this. So let me jump ahead where that's at. View, page display, scrolling, okay? So here's what it looks like inside of ElectroSmash. And when we start to ignore these things here at the beginning, then we just have this end up happening where we have V out right here, going through these components to a VN node that's right here. And then we have VN through this, across this capacitor and across this resistor right here. So I've ignored these things as a way to simplify our lives. I'm also going to substitute in for these pair of diodes right here with VD. And then I'm going to substitute in for this capacitor with the decay method for both of these right there. Also, a thing that I'm doing is this potentiometer that is set up to control the distortion is done so that we have this wiper across the resistor that effectively just bypasses the resistor and allows us to just have 51 kilo ohms happening up here on this branch, or we can bring in more resistance on this branch too. What this is going to do, to give you some intuition about it, is the less amount of resistance we have on this path, the more current is going to be able to flow through this top path where there's no distortion, where there's no clipping that is going to happen through this one. But if we put more resistance on this path, then there's more current, more of our signal has to go through these diodes, which means that they're going to be saturated more. So by effectively having this resistor right here, or potentiometer, be something where we go down to no resistance or up to a high amount of resistance, we're able to control the amount that of our signal that has to go through the diodes, or the amount of the signal that's allowed to go around the diodes, because the current isn't hitting a lot of resistance up on this top path. So that's some basic intuition about how this ends up working as a control for the amount of distortion. Okay, so this is what the circuit ends up being reduced down to right here, and like this. And now we have a voltage divider where we have the out is the total voltage from here all the way down to ground. Then we have VD is the voltage from V out down to VN. And then we have VN down to ground as the other one. Okay, so I do a lot of algebra that I've shown you before. We have the total current going through the whole thing. So this is where we start to use our nonlinear equation for it. And eventually we end up with this big long equation right here for our voltage as a function of our input and the voltage across the diode, that we can take the derivative of this with respect to the voltage across the diode as a way to solve for it. And that's what we have. This should be cosine, not sine. That's an error on it. So that's our derivative that we can use in the Newton-Raphson method. And then we have these state update equations. When we have capacitance, we need to update the capacitors after we find our VD or we find our V out for it. So we still need to use that decay method to update all those in it too. So these are the equations for V2 and then also for V1 that we'll end up doing. So let's switch over to the code that's already completed, and we can see it in there in the JUCE project to have that to just finish things up. So let me talk you through this. Most of the stuff is just set up, plugging in the values. These are the constants that we're going to set for our diodes. These are our values of potentiometers and capacitors and resistors, and some combined resistances that I'm calculating here are states. Again, if you want to make this stereo, turn these into arrays. And then we're initializing our VD. You probably actually want to initialize this for both the left and the right channel too, so that your left channel is picking up where it left off and your right channel is picking up where it left off. And then I made this threshold that we'll use for the Newton-Raphson method. Okay, so here is where all that is happening. Okay, so I calculate a thing that doesn't change. There's a part of our equation that is not going to change based on VD. So there's a part that does change based on VD. There's a part that doesn't change. So as a way to make it a little bit more efficient, we can calculate the things that don't change based on VD ahead of time. And those will stay the same, and that's just a single variable. Saves us from some divisions and some multiplications and additions. So we've saved that in here. So this is my function of VD. So that's the main function that we want to check. And we're going to check if this absolute value of it is greater than the threshold. So if it is greater, that means we have a problem. We need to change our value of VD. And so we do that in here by calculating the denominator like this. And then this is where we get into the damped Newton-Raphson method, which I wish I had more time to cover. But basically, you do some extra checks inside of here to see if your value that you're calculating is getting worse or getting better. If it's getting worse, then you scale it down by this B value. You start out with B equal to 1, but if there's a problem with it, then you reduce it down. Let me maybe draw you a picture of what this looks like to explain it really, really quickly. So if here's what we had before for our Newton-Raphson method, where we start out over here and try to get down to a point here through these different steps like this, we could have a function that's a problem where maybe it's curved like this and our initial guess is way up here. So our slope that we end up using puts us way, way, way off over here on our function, where then if we find the slope of this one, it takes us off in the other direction. And now we're diverging. We're not getting closer to this one. We're getting further away. So the idea of this damped method is to scale this down by a half and say, well, let's start from right here and take this slope and see if we use the same slope as above. Maybe this gets us closer. Maybe it doesn't. If it doesn't, let's keep going down and use this slope again until we get to a point where, okay, we're getting closer to 0 and not further away from it on it each guess. So this is what the idea of the damped method is, where you take this slope and you multiply by a half each time to keep going down to smaller and smaller values until you get closer to 0. So that's what this value right here for B ends up being. So then we calculate a new version of that function. And if it's good, then we're great. We can save that as our VD value. But if it's getting worse, then we damp it down and keep trying to try new ones over and over again. Okay. So if we find a good VD value to use, we will save that and be able to use it back through our derivative again and continue these iterations until we're less than our threshold. And when that's true, then we calculate a V out. So a tricky thing about this circuit, if I'll show you from these slides, is that our V out is equal to the combination of the voltage across the diodes plus the voltage across the input. So our voltage across the output is not just equal to VD, it's equal to the sum of these things. So, oops, I did something here by accident. So we need to sum those things up. Then we do the state update equations for X1 and update those. And now we have V out. So everything else on here is just updating the knobs, updating the parameters like this, updating the pots for the coefficients. And that's the gist of it. I guess it's worth trying to build now. It's having an issue with different versions of JUCE on my machine. I'm sorry about that. So I'm going to build it separately and then load it in there and see if this ends up being better. Hopefully it doesn't crash logic. So I hope you all, if you're trying to get this, can build it. Again, if you've got questions, I'm going to hang around afterwards, people to discuss it. And maybe there's some parts that I should focus on more based on everyone's feedback on it. I can also remind you again, I've got a much longer form version of this workshop. Instead of trying to cram it all into 3 hours, it's spread out over 16 hours that I can share with you if you are really into this analog modeling stuff. I've also taught it as a university course. And if you're really interested in that, I have private YouTube videos of a whole course on this that you could contact me about. And I'd be happy to share those with people that are extremely interested in this stuff and willing to take the time on it. So let me see if I pull up logic where we're at on it. Okay. So I'm hoping that this is coming through Zoom. Let me check the chat. Technically, I'm not hearing this through my computer. Can't hear the audio. It's not. No sound. Let me try this. Preferences, audio. I promise we tried this beforehand, but then I turned restarting. It's not working. Sorry about this. This is very frustrating for me as much as it is, I'm sure, for all of you. Audio is happening here. Let me try to turn off Zoom audio and then turn it back on. Let me try to share the screen. I thought I had enabled it all along. Try to share my audio. Share sound. Yes, that is the issue. So every time I turned off share screen, I lost it. So here we go. Yes. All right. Thank you. Thank you. So let me experiment with some of the settings. Here's the drive. Turn down the output. So I won't play back any more audio here. I can tell you from analyzing this, and I have the scripts if you're interested in MATLAB for it. And also, there were some people that participated in my workshop before that ported most of this stuff over to Python. So if you work in Python and you want to see some of the analyses done in Python, it's there in MATLAB and Python for it. We have the correct frequency response. So the result that you have in the version here ends up having these values for the different knob values of all treble and all bass. And then also, like, it ends up with this, if you put it in a sine wave, you end up with this cool analog modeled weird distortion shape that you can't just get with a basic wave shaper. So we're coming up on our time here to close. I will hang around afterwards and also jump over to the Discord if people want to talk. I'll try my best to answer some of the questions that are in the Q&A, and I will stop there for my presentation. And if people want to jump on and ask questions on their video, that is fine with me. Or also if they want to type them in, I will try my best to either answer them over my voice or type them in. So let me answer some things on here. Okay, so how can you get in touch for the longer workshop? So one way is maybe just over Twitter. On Twitter, you can send me a direct message. My Twitter handle is Hack Audio, H-A-C-K audio, one word. And send me a direct message there, and I'll get in touch with you over email then from that point, and we can set you up with the materials for that. I have it both on my website, which is hackaudio.com, and also I have it on a Patreon page if you want to access them on that. But I'll make sure to set you up if you're paying for the ADC. I'm not going to make you to pay for the workshop over again. Is there a chorus course? So I don't have one that's modeling like a Bucket Brigade analog chorus that I've done. I can send you materials on how to implement like a digital chorus, but there's nothing I've done that's like an analog modeled one that at least is not proprietary, that I am under obligation to not share with people. But I do have a textbook, and it's called Hack Audio. And if you find the textbook, it has a whole chapter on modulation effects on how to do chorus, flanging, phasing, and those things, just digital implementations. But if you're really interested in analog chorus, my recommendation is to find this paper that came out a few years ago on modeling bucket brigade delay and getting a model for that going, and then using that. So if you're really interested in it, again, shoot me a message on Twitter and I will connect you with the papers. If there's stuff and questions from the workshop that you asked, where's the paper that's on the DK method, send me a message on Twitter and I'll find you all these papers and connect you with them on it too. So I'm happy to continue, corresponding with people if they have, big picture questions about how do I create this whole other kind of thing. Another thing I'm seeing on here, are lookup tables a good method for optimization to replace an in-Rapid method in this case? Yes, in this particular case, it is. So in this particular circuit, we basically have a one-dimensional, or not one-dimensional, I guess it would be, yeah, we just have this a single variable that we're taking the derivative over. And so if you have that be the case, then a lookup table is fine, where you're just going to have, a lookup table for a bunch of values of Vn. You get a value of Vd that you can use. Now, that only really works when you have a relatively simple circuit. As soon as you start having a transistor in it, where you have multiple dimensions of things that you're trying to take the derivative over, then I think the lookup table is going to be impossible to really fill and take into account all the possible combinations of things that could be happening. I guess I didn't really think through it could be complicated because we have states in this too. So because we have states, this might be one where it doesn't work so well, because each value of the state in combination with each value of the input voltage is going to be things that you have to have a table to look up all these combinations of all these different things. So the lookup table can be advantageous in certain cases, but also can just be massive in other cases too, and difficult to find all of them. So questions on here. Why do we need an input-output buffer in the analog domain? Question was about just the general sections of the tube screamer pedal. So in that case, we don't want to have loading that happens or interaction basically between one pedal and another pedal. Ideally, what we like to have is each pedal act in isolation, where you're not having the circuitry that's happening inside of one pedal change the behavior of something outside of that. And so we usually have these buffers, either in the form of op amps. So op amps can be used as a way to buffer different blocks of your of a circuit on it, or you can also use transistors as another way to do it. And so that's what we're finding that's what's found in the tube screamer, is you have an input and output buffer that basically allow voltage to come in, but block current from being pulled from a different thing, presumably outside of the pedal on that. So great question. All right, let me see if there's other stuff I can hit on here. DMs are closed on Twitter account. However, oh, sorry, I didn't realize my Twitter account has things closed. Let me change that today. If I don't know why I would be blocking, I don't get DMs from people. I'm not like someone that slide into your DMs. Anyway, let me do that. I'll also jump onto Discord, and maybe the simplest thing is, look, there's only so many people on this chat. I'll put my email address down here and just email me directly. So my email address is down here. I trust that people are not going to spam me with crazy stuff, but maybe the easiest way to get a hold of me is erictarr@gmail.com. Just jump on that and email me directly. I will be much more responsive to email than I will be on Twitter anyway, because I don't get on it very often. So email me and I can just give you some resources more about this stuff. And you don't necessarily have to feel like you have to do it right after right after the workshop. If you email me 6 months from now, I'll still be happy to connect with you, and grateful for your interest in my workshop and all that stuff too. So feel free to just, add that to your address book or anything, and contact me if you have any questions about analog modeling. So question on here about a lot of weird distortion sounds besides the pleasing distortion. So from Jeff, if that's the case, yeah, there's probably a thing where I didn't make it a stereo processing. So you might want to add stereo processing, where you basically go through and make X1, X2, and those states be stereo. Yeah, that's probably a number of people that came up with issues. I apologize for not having that set up ahead of time. I was trying to rush things very quickly. So yeah, if you're comfortable and you have an idea with doing the programming to make it stereo, I think that's the way to go to solve some of those weird things. Thanks to everyone for your interest in this. You all think it's better to hang out here in the Zoom chat? I'm fine with staying here. I can head over to Discord. I can do any of those things if people want to continue the discussion. I think we have at least the next workshop would start at the top of the next hour. Track host is telling me, let's switch over to Discord, and we'll wrap up what's happening here on Zoom. And I'm grateful for everyone that was interested in this. I know we went through things at a breakneck pace. So I hope the resources that I at least introduced to you and stuff that's provided in the notes and the things are enough to help you continue down your interest in analog modeling and turning those things into plugins. So thanks a lot, everyone. I'm switching over to Discord.